Hi, welcome back to AP Physics 1. Here we are still talking about rotation again, last unit of the year. So this is what we call here CAAKE, right? So back in unit 1, right, we had the CAAKE equations, right, which we called, right, the constant acceleration kinematics equations. Well, just like we did, constant acceleration, right, kinematics equations. So just like in the last video where we talked about that there was, rotational equivalent to linear, we do the same thing here, right? So much like linear motion, there is a set of equations that assumes constant angular acceleration, right? And so that's where our double A comes from in our CAAKE equations, right? So we call this set of equations the constant angular acceleration kinematics equations. And there's going to be a very easy transition from the single A CAAKE equations to the double A CAAKE equations. And that's simply just changing the variables so here's where it's easy, right? We just change the variables. So we're going to go from our linear variables to our rotational variables. Okay, so if we think about the kinematics equations, we got V equals VO plus AT. We have delta X equals VOT plus 1/2 AT squared. And then we have V squared equals VO squared plus 2A delta X. And then we have delta X equals 1/2 V plus V0 times T. Right, so those are our constant angular acceleration linear equations, right? So now how do we change it to rotational? So remember, V is omega, A is alpha, and X is theta. So that's all we're going to do. We're going to replace V, A in X, and T is T, right? Time doesn't care if you're going in a straight line or if you're rotating, okay? And so we're going to substitute. So instead of it being V equals VO plus AT, it's going to be omega equals omega 0 alpha T. Again, just flip-flopping linear to angular. So delta theta equals omega T plus 1/2 alpha T squared. And then omega squared equals omega 0 squared plus 2 alpha delta theta. And finally, delta theta equals 1/2 omega plus omega 0. Sorry, it's a bad omega. All right, so omega 0 T. Now, remember, the equations, all right, and so all that stuff that we talked about linearly, remember we talked about graphs, right? So V versus T. Sorry, I apparently hit the home button. So we got V, sorry, I put the flip-flop those. So you have T and V, right? Position, we have those graphs, position time, velocity time. All that stuff also holds true here, right? So if I have a V versus time graph, the slope of the graph is acceleration, where the area, right, under the graph is my displacement. But same thing happens, right, if I have an angular speed versus time, right? The area under the curve is the angular displacement, and then if I have if I find the slope of that, it's the angular acceleration. Okay, and if I have the position time graph, same thing. The slope of a position time graph is the acceleration. If it's a parabola, then it's accelerated. If it's a straight line, it's not accelerated. Okay, so let's look at an example problem. So a centrifuge in a medical laboratory is rotating at an angular speed of 3,600 revolutions per minute. When switched off, it rotates 50 times before coming to rest. What is the constant angular acceleration of the centrifuge? Okay, So one thing to remember, the first thing is this, right? So that's the famous unit of RPM that you see on cars, you see on record players, but it's not our SI. So our SI is radians per second. So I have to do a quick conversion factor, right? So 1 revolution is 2 pi radians, and 1 minute is 60 seconds. So that's going to give me my 3,600 revolutions per minute in radians per second. So I do 3,600 times 2 pi divided by 60, and I get 377 radians per second. Now I can go and do my, I can do the, excuse me, I can go, I got to do one more conversion, right? It says it rotates 50 times. But again, I need this in radians. So I have 50 rotations or 50 revolutions. So 1 revolution is 2 pi radians. Okay, and so that tells me I go so I have an angular displacement, of 314 radians. Okay, it's basically 50 times 2 times pi. So that gives me 314 radians. Now I have the information that I need that I can start with or solve my problem. So I have omega squared equals omega initial squared plus 2 alpha delta theta. And what I'm going to do is I'm going to solve it for alpha. So alpha equals omega squared minus omega initial squared over 2 delta theta. Well, my final, right, I'm coming to a stop just like we did in linear. We can cancel that out. And so I have negative 377 squared over 2 times 314. And again, the negative sign is because we're coming to a stop, right? And so my alpha, put it up here, is equal to negative 226 radians per second squared. So that's the rate at which it comes to a stop. Okay, again, the negative sign means it's coming to a stop. Now, in the next video, we're going to switch our thinking from kinematics to now to more dynamics and talking about torque, moment of inertia, and then rotational dynamics.